Hi, everyone. Welcome back to Bufnagle the podcast, where we explore entertaining and enlightening discussions of the adventure of life and all things good. From science and technology to history and philosophy to leadership and success. We hope to give you a better understanding of the world and skills for everyone to pursue their own adventure.
All you need to do is just hit the button and start recording.
I should do it every time. Okay, so I walked into the room, okay, and then I had to close the doors. And I want to there's the slidey doors, right? So I wanted to close them without them banging really hard against each other. So I set my drink down there behind my monitor. And then when I walk around it, I found it here. And there it is. So
good. I'm glad.
So
for all the listeners out there,
it is old
we had
age.
we had probably 3 to 5 minutes of good conversation before I told Rafe, "Hey, hit the start button."
Yeah, and now you have to listen to the not good conversation.
Yes, now all of the good conversation has been passed away by time, and now you're stuck with just regular Bufnagle content.
There you go.
But welcome back to The Buff, where we talk about all things good in the pursuit of the adventure of life. I'm Harry. I'm hosting, this is the listeners don't know, this is our fourth recording night in a row.
Yeah, so we're doing this because we're working to get ahead for when I'm out gallivanting across the globe doing my summer vacation.
Glorified vacation.
Yep. My summer school, Harry. It's summer school. And we're putting them back to back, but they're going to come out. I think this should be, if it drops right, this should be episode number 200 on The Buff, which is a milestone. But it's not exactly right because there are some episodes in there that are like special edition episodes.
Kind of like Star Wars holiday special or whatever.
Yes. Didn't they have a Christmas special? Wasn't there a Star Wars Christmas special where they were singing and dancing around the, I don't know, Darth Vader tree or something? Anyway, Harry, it is a great day to be doing a podcast with you again. And one reason this is a great day is we have great listeners. We are a global top 10% podcast because of our listeners. As usual, please reach out to us at bufnagle@bufnagle.com. Share the love, share the buff. Remember, a 5-star review does a world of good for a world of people. Subscribe, hit the smiley stars, hit the follow button. Tell a friend to listen. You will get a free episode. You know what? Call your folks and say, hey, you know what? Listen to
Guess what I was listening to, yeah.
And if you're a mom who has kids, call that, because kids always do what their parents tell them.
And your kids will learn something,
and
like they will today.
Yes, they should learn something today because we are...
If they can comprehend it.
Holy cow, because this gets... Harry, this is our last one on light. And some of you are...
listeners like, oh, thank goodness, I can just wait till next week.
Oh, great. I'll fast forward and come back in a week. But no, we've gotten some good feedback on the light thing. People, I never know what to do with this, right? We've had a lot of conversations. Do you like when we kind of go down rabbit holes of things? Do you like them to be, when there are multiple episodes, do you like them all bunched together like we did with Shackleton last year?
Yep.
Or do you prefer them kind of spaced out? And I kind of like them spaced out because that's kind of how I view the world. I think is it's hard. I have a hard time staying focused on that. And if I get a little disinterested or I lose track of where I am, I was like, what? How come we're talking about light again? It's been like 4 weeks in a row. So we're doing it this time. We're spacing them out, and we've done that with some of the historical ones. Shackleton we did less. So here's the thing for you. Go back, listen to what is it, 5 or 6 episodes on Shackleton?
I think it's 6
all in a row, and then listen to the big grand thing about light, all of them in a row, but with the other things sprinkled in it, and see which
one. A little bit
like
of Buff-Niggly goodness sprinkled throughout.
There is it. You know what we need? We need Bufnagle to now come in spray cans. And I have a little video to show you of. Do you remember King of the Hill? Do you remember the TV show King of the Hill with Hank Hill? And I think the video was entitled something, "This is the most dad mode thing ever." And it's Hank Hill like kneeling down working on a doorknob or something. and he reaches down to grab the can, like a can of some kind of spray can. He's trying to get the top off and he can't. So he reaches into this holster on his belt and he pulls out a little can of WD-40 and goes, shh, and he sprays it all over the lid of the can and he goes, and he pops the lid off the can and he takes that can and he sprays it in the doorknob because it's a can of WD-40.
So what else is it?
Yeah. So anyway, I thought that was kind of funny, and I think that of that a lot. If it sticks and it's not supposed to, then you use WD-40, and if it doesn't stick and it should, then you use duct tape.
Yeah, it solves like what 90% of your problems.
Well, it does solve a lot of them. That does your garage door squeak? How long have you been in your new house?
It does squeak. Yeah, I'm glad you mentioned that because I was thinking it. And Jamie goes, we should really use some WD-40 on the garage door. I don't even know where to put it. Just everywhere?
No. Well, okay. So there's any
place
where things you could dip the whole garage door in it.
Right.
Any place where there are moving parts. So like there's that pulley on the side, and it has that axle in it. Where that pulley spins around the axle to do that. But that axle also sits in a housing, and it can rotate. So it goes in there.
And then there's along the rail system for the wheels.
Well, no. Well, the wheels roll in the track, and I don't think I'd need to put it in there, but I would put it in. There's also the hinges between the panels, and they're under a lot of stress. I mean, the garage door is a heavy thing. That spring is doing a lot of work, and that's metal grinding on metal, and it'll start to squeak, and just a tiny little squirt. Get that. You get the can with the long red.
It's got the red tube on it.
Yeah, and now they come with the red tube. Actually, as part of
there's a scoop.
Well, no, there's a scoop. It comes in a spray bottle. No, it has the red tube is on like a little hinge thing, so it doesn't pop out. Just folds up, folds back down. Innovation in spray can delivery.
Only the best for the United States of America.
Yeah. Oh, there we go. We just have a lot of really great stuff. And, Olivia was saying the other day, because she came over for her birthday, we did a little bike ride on her birthday, and she forgot her helmet, and we had a helmet here, and the helmet has a little knob you turn on the back, and it tightens around your head. And it was just, she was like,
they're fantastic.
Yeah, that's what she said. She said, I remember being a little kid, and so there's an invention over the last 15 years of not a lot of, it's like we still had things. We had bike helmets and they worked, but it was always this, different thickness of Velcro pads and stuff like that. And now we just tighten that thing down and bingo, we rode all the way up to Sheridan back on the Monon Trail.
Yeah. How far did you go?
Oh, I don't know. It's about 5 or 10 miles. Wasn't very far.
So it wasn't tandem biking with dragging her along.
No,
nothing against her, but I'm sure it was.
Well, she was younger and she was smaller, and we did the tandem across the state of New York, and it was a lot of work, but it was all good. I would do it again in a heartbeat.
I'm sure your balance got a lot better, collectively, right?
Well, a tandem bike is really heavy. Okay. And I remember when we had one of these gigantic hills going through one of those big valleys up there, and that bike, a tandem bike weighs a lot. And then you put me on there and her on there. That's at least 250 or almost, 200, between 250 and 300 pounds of persons. And then we had all our equipment in the bags on the back, and the bike itself probably weighed, I don't know, a really nice bike weighs 25 or 30 pounds. I'll bet the tandem weighs 60. I mean, it's really heavy. And I tell you, we were roaring down this mountain, and it was just like, it was smooth as, there was no need for any, it balanced itself. Gyroscopes, man. Those wheels did miraculous things for us. So it was a good bike ride.
Oh, good. Well, we're going to talk about bike rides and going really fast, right? Because that's what we're talking about here.
Yes, we will.
Provided we have enough time. So let's just get right into it.
Well, you know what? If we don't have enough time, we'll just go really fast, and time will slow down, as you can see coming up. Okay, so we've been talking about light, and we'll come to a grand conclusion at the end. But recently, we're talking about special relativity. Talks about the speed of light c being the same in all inertial reference frames. And this leads to two interesting conclusions that we're going to discuss here tonight, and that you can get to them through what Einstein called thought experiments. So thought experiments are you just kind of reason out what will happen and you get there. So in Einstein did them in physics with the light sorts of things, and we do them all the time. If you've ever taken a statistics course, a lot of statistics is done in the context of thought experiments. So we say, imagine you're flipping a coin 10 times or 100 times or 1,000 times, and you look at a theoretical distribution, and that comes from a thought experiment. So Einstein did these thought experiments. He posed a situation and he said, let's reason out what will happen. So he says, let's measure the speed of light in two inertial reference frames at the same time. Now we know we should get the same answer, but they can be very different depending upon how you set up the problem. So, and remember, a lot of this stuff comes from our friend Michael Fowler at the University of Virginia. There's a website there. If you type in Michael Fowler, University of Virginia physics notes or something like that, this is almost all these notes are from his course number 252, which is on advanced physics stuff, and also some standard textbooks, physics textbooks, and two other books here I'm going to mention here that I've used along the line here. One of them is one of my favorite Einstein books is Einstein's Clocks and Poincaré's Maps, Empires of Time. It's a discussion of Einstein's clocks.
I like how you displayed that to me as if all of the listeners could see it.
But it adds to the, like, if you close your eyes and listen, you can probably hear the book here next to my head. And then the other one is, someday we will go to video, and this is how it will differ, is you'll be able to see me holding up the book. And then the other one is this book, About Time, Einstein's Unfinished Revolution, and it's by Paul Davies. So amongst those things you can put, and then our friends over at Wikipedia and all sorts of other, there's a lot of stuff out there on this topic. And for what it's worth, you can do all the Einstein correction stuff in undergraduate physics things for doing like the GPS satellites and things. I mean, so it's within reach is what I'm saying. You don't need to be an astrophysicist, but it helps. And if you are an astrophysicist, you've already gone through this. So Einstein said, let's suppose we're gonna measure the speed of light in two inertial reference frames at the same time. Now, suppose we have a really, it's going to have to be big because we're going to be moving very fast. We have a flat piece of ground and a flashlight that emits a blip of light, just a single blip, a blip or a blink or whatever you want to call it, just a little dart of light that shoots out of it. And on the ground, we have two photocells. So these are your classic photocells. When a light beam hits them, they react and they send a signal to do whatever a signal does. So and we're going to place them 10 meters apart in the direction of that the light blip is going to travel. And each one will register when the beam of light hits it, and it's going to send a signal down a wire to a clock that tells you what time it was when they hit it. So these two photocells are 10 meters apart. So the light's going to go, it's going to hit the first one, it's going to hit the second one, and the computer is going to measure the time when it hits them. It's a very accurate little clock we have on the backside of this thing.
Yeah.
So we'll be able to determine the light or the time it takes for the light to travel from the first to the second photocell. Okay, so call it time t.
That should be, I'm guessing, the same amount of time it takes from the beginning to spot one.
Well, we're just going to, it's going to start off to the side. We could say that it will be if the first photocell is 10 meters from
but they are some distance down the way, but the separation between the photocells is 10 meters.
Yeah, it's just going to go along. So we're going to call that time t. And based on that time and the distance between the photocells, we can use that to determine the speed of light. We can say that the speed of light will be c, which is 10 meters divided by t, right? Because distance equals rate times time. So then rate must be distance over time.
Yep.
Okay. So now we're going to put somebody else. Okay, maybe I'll be standing on the ground and you will be the courageous entrepreneur, and you're going to be in a spaceship passing overhead, traveling at half the speed of light. Right? And you're going to be going in the same direction as the light beam. Okay? So you're kind of passing overhead. And what we're going to do is we're going to paint two other photocells we're going to tape them to the very, very good duct tape, right?
That's right.
We're going to tape them to the bottom of your spaceship, and we're going to space them 10 meters apart on the bottom of the spaceship. Okay.
So both of them are moving with my spaceship.
Yes, they're moving. And they are moving then at the speed of light over 2. So these can measure the speed of light relative to the spaceship.
Yes.
Okay, but the spaceship's moving. Okay, it's moving
pretty fast.
At half as fast as it possibly could go. Right?
Sure.
Surely CO2. Okay, so and it turns out that if you measure that time between for that spaceship between the light beam hitting the first one and the light beam hitting the second one, it's still going to be the same amount of time. It's 10 meters between them. It's going to be the same amount of time because regardless of the velocity that you are traveling at if you're in an inertial reference frame, the speed of light will be the same. And so even though the ship is traveling at half the speed of light relative to you standing on, you are traveling half speed of light relative to me standing on the ground, our measurements of light are going to be the same. And what you need to do is compare how this would be different if instead of shooting a beam of light, we were shooting like a cannonball. Right. Okay. And we had special cannonball detectors. Okay. So
usually that's just like the ground or a person or a vehicle at the other end of the cannonball.
Right.
But usually then they can't send a signal back.
Yes. You kind of wait for the explosion. That's kind of the signal you see. So if you shot a cannonball at a certain velocity V relative to the ground, then the first person would see, the person standing on the ground would see it traveling at V. But the spaceship zooming along, now keep in mind, it's moving away from the cannonball at C over 2. But then the cannonball is moving at V, so you would get negative C over 2 plus V. You would get different rates for that, for the cannonball. But you get the same rate, the same time, right, for light. So that's a consequence of it doesn't matter how fast you're going. The light beam appears to you to travel at the same velocity. Now let's do something complicated. Again, this is where this is actually
because the first example wasn't complicated enough for the casual listener.
Okay, so this really started a long time ago, probably close to a year ago. Zach asked me, "Tell me about time slowing down when you start going real fast." And I started to try to explain this, and I didn't do a very good job when we were on the phone one day like that. And we went. I said, "I'll have to read about it, and I'll make an episode." Right, and it's now turned into 5.
So that's how I got wrapped into that.
Yeah. Yes. So that's how you got wrapped into this. So now we're going to build a clock. Okay. So imagine this. It's called a light clock. And it has, imagine 2 horizontal mirrors. Okay, so they're flat mirrors, and they're laying facing each other. Okay, so they're flat. So they are light.
So one is on the ground and one is on the ceiling.
That's exactly right. Right. One's on the ground, one's on the ceiling, and they are a distance W meters apart. Okay, pick a number you want. Maybe 1 meter, maybe 10 meters. There's distance apart vertically. Okay, and we're going to set up this magic flashlight thing so it can send a blip of light bouncing back and forth up and down between the mirrors. Mm-hmm. It's going to bounce. It's going boop, 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 like in a video game.
It's just playing Pong over and over.
It is playing Pong. That's right. Exactly. That's what it's doing. It does Pong, but it does it. Of course, the light beam is traveling at light speed. All right. So now, and also imagine that in the top mirror there is a light sensor that detects when the blip hits the top mirror. Okay. Mm-hmm. Right. And this light sensor records the blip hitting the top mirror, and every time it hits one, it turns a rotor that makes a clock go. So this is a light clock, and it's just using the bouncing back and forth of the light beam to drive the rotation of the hand, so to speak. Okay,
got it.
So this records the blips, and they drive a clock rotor. Now, if the mirrors are 1 meter apart, then the recording will trigger once every 2 over 299,792,458 seconds. right? Because it'll go up and down. It'll travel 2 meters, which is 1 over the speed of light in meters times 2, because it had to go up and back down. Okay, right? Or it's going to be 6.67 times 10 to the minus ninth seconds for every one of those. Okay, so it's going really fast up and down because it's speed of light thing, right? Okay, so it's going to blip like 100 and just short of 150,000 blips every second.
150 million.
150 million. Thank you. See, this is exactly why you're that. You keep and
just so you can get.
I'm just off by an order of magnitude.
Yeah,
3 times.
Yep. Yeah, no big deal there. All right, so the light pulse, the Einstein's pong is going back and forth a whole lot.
All right, so in general, the time between clicks, remember, click every time it hits the top mirror. Click, 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 click. All right, the time between clicks is 2w, which is twice the distance, over c, because distance equals rate times time. So the time between the clicks is 2w over c. Now, we're going to have 2 of these clocks. And one of these clocks we're going to give to Abe. Mm-hmm. Okay. And Abe is, and the other one is going to be given to Betty. So Abe and Betty each have a clock. And they each take that clock into their favorite inertial reference frame. Now, Abe's clock and Abe's reference frame is the solid terra firma that I'm standing on right now. All right. It's right outside my house. There's Abe's clock and his reference frame is sitting right there. Right. And it turns out that we're going to put a special rail line in so we can drive a train across my reference frame. And on that train, we're going to have a large flat car, a train car, that Betty is going to stand on with Betty's clock. Okay.
All right.
Okay. And this flat car is going to move down the track at velocity v. Okay.
Got it. Yep.
So Abe is standing on the ground with a light clock. Betty is on the train car with a light clock. Betty is moving relative to Abe. And quite frankly, Abe is moving relative to Betty. It doesn't really matter which way you look at it. We're going to start with Abe on quote, terra firma, solid ground. Because that's
how we've got it set up.
That's how we set it up. Okay, so now Abe is going to check the ticking of Betty's clock relative to his clock. Okay, so he knows that his clock is ticking once every 2w over c seconds. Okay, it's clicking pretty fast, but he knows how often it's ticking. So he pulls out his binoculars and he starts watching Betty's clock, the little blip going up and down on Betty's clock. Right,
because it's the same clock.
It's the same clock. It's essentially the same clock. Yep. All right. And he's watching the little light beam going up and down. Now, the question is, how long does it take Betty's clock to go up and down to make one tick? And you're like,
it should be exactly the same.
Of course it should be, because they are the same clock. But Betty's moving really fast, okay, at velocity v. Now, Abe knows that light is traveling at 3 times 10 to the 8th meters per second. That's Einstein's special relativity. He knows that her clock has that light beam on it and it's going at that speed. And he's measuring it because he's in a reference. There it is. It's constant. So he knows the velocity. The question is, what's the distance that light travels? Now, at first blush, it appears, well, it's going up and down. So it's traveling 2w, right? Whatever w is, it's going up and down, back up and down, up and down, up and down. But it's not going straight up and down. It's actually making a zigzag pattern because the train is moving down the track. Okay? It's moving down the track. The mirrors are moving relative to the ground, and the blip is following a zigzag pattern. Now, to Betty, it looks like it's going up and down. But to Abe, sitting on the side, he's watching a tick, 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 tick. He's watching a triangle wave move along. Okay? So from Abe's point of view, the light beam is moving forward as it's going up and down, bouncing between the mirrors. So from his point of view, it's actually going farther. So how far is it going? Right.
Well,
so
I think Pythagoras can tell us this, right?
Pythagoras is going to tell us this. Now, suppose Abe measures the time for the blip from the bottom of the top of the mirror. Call it t. Right? The distance from Abe's point of view must be c times t. That's how right? That's c times c. It's the rate times the time, right? Since c is constant. But the mirrors have moved down the track during that time t. And the mirrors are moving at velocity v. So the mirrors have moved at vt horizontally, right? So we have a triangle where the horizontal component is v times t. The vertical component is, the diagonal component is c times t. And the vertical component is going to be w, right?
Right. Yep.
So Pythagoras steps into he's always hanging around. All right. So he walks up to Abe.
Yeah,
He goes,
you didn't think that triangles were going to be important back in 7th,
right.
8th, 9th grade.
So Pythagoras comes up and says, Abe, I can help you out. Of course, he says this in Greek, right? He says, I can help you out. I know that CT squared, the quantity CT squared, is going to be equal to VT squared plus W squared. And if you do the math on that, you can solve for T. And what you get is T equals W over C times this quantity times the square root, over the square root of 1 minus V over C squared. Okay, it's a square root 1 minus quantity V over C squared. That's the time it's going to take for Abe to see Betty's blip go from the bottom to the top. Okay? So for the full-on one lap around or time between blips, from Abe's point of view, it's going to be twice that, right? Because it's got to go down and then up. So Abe is going to get, for Betty's clock, when he's watching Betty's clock from a distance, it's going to be 2W over C times 1 over 1 minus V squared over C squared.
Right.
Okay. Yep. Now note, if V is 0, if Betty's just sitting still, then that second piece, 1 minus V squared over C squared, that's just 1. It just goes away, right? So you get 2W over C, which is the same as his clock. So when they're sitting there, and this is why we need to go to video here. You can see my fingers going up and down and up and down and up and down because they're in phase, all right? So you get the same as for Abe's clock and Betty's clock. But if V is not 0, then Abe will see Betty's clock running slow as it takes longer between clicks.
Right. So if they start at noon, and we'll say that this train is very long and Abe can see a very long distance.
Yeah.
He will see the train, for his clock, the train passes from noon to 1. But on Betty's clock, he sees it running slow. So by the time the train reaches the end of his view, it only says 12:15. Or
something. Yeah, it says less than 1 o'clock.
Right.
And now you can compute exactly what it will say. And we're not going to go into that because what happens, a lot of equations are going to start coming, and I think a lot of them already have. And if you're driving right now, and I realize you're taking notes on that napkin,
Yeah, right on the steering wheel, and you're honking probably a whole lot too with all these exclamation points.
Yes. So we don't want any problems while you're driving, but you can compute that with this 1 minus V squared over C squared thing, this extra factor. Okay, so now we used a light clock here with this up and down blippy thing because it's easy to see that from a,
Yeah, it's easy to see.
We can see it from a different reference frame. But any and all clocks, anything that works through time, regardless of type, that Betty has on the flat car will keep steady time with the light clock, and it will fall behind Abe's point of view by a factor of the square root of 1 minus V squared over C squared. All time to Betty will appear slower to Abe. Betty's time appears slower to Abe, which is mind-boggling in a certain sense. Okay? But it gets weirder.
Yeah, it gets better.
Okay?
But wait, there's more.
Okay. Now let's look at it from Betty's point of view. Okay. Betty's on the train car. She's got her little light clock. Might even have a latte there and maybe a book that she's reading. But okay, she's on the train car and
she's hanging up on the rail car. Yep.
She's on the rail car and she's moving at constant velocity, c over 2. Right? Just like she was doing in this. Did we put her in the spaceship before? Anyway, she's in the spaceship.
Or I was in the spaceship. She's on the rail car.
Okay. Yeah, okay. So she's on the rail car.
I'm only traveling at c over 2.
That's right. Well, she's traveling at v, whatever it is. Okay. Betty's inertial reference frame is just as valid as Abe's because she's at constant velocity. So from her point of view, she's sitting still, essentially. And it's Abe that is moving backwards relative to her.
Right.
Right? So when she looks out and sees Abe's clock, she sees Abe's clock making the zigzag path. And she does the same math that Abe just did. Right? And from her point of view, it is Abe's clock that's running slow. Both Abe and Betty see the other's clocks ticking more slowly than their own.
We'll give the listeners a pause here to think about it.
Okay. Both of them see the other one's clock running slow. Now, what we could go into, and we won't, because this has to be a finite. This episode has to be finite, as does
the series.
As does this series. It has to end somewhere, all right? And what I'm going to do is encourage you to go to the Fowler notes I mentioned previously and continue to read up on this, because it gets very wacky when you send Betty out on a long distance journey to some planet far or some star far away and then have her come back, and how they communicate to each other. Time slows down, and then some other really, really weird things happen. Okay, this is called time dilation, meaning that time it ticks more slowly. Things get stretched out. Okay, and they've demonstrated that this is a real thing. It's not just a thought experiment. You can take very accurate clocks, these atomic clocks that they have, and they put them in airplanes and they fly them around really fast, and then they come back down and compare them to the ones that were just sitting on the ground, and they have appeared to move slower than the ones that were sitting here flying.
And we're not talking like minutes slower, right? We're talking like nanoseconds.
Nanoseconds. Yes, exactly. So, but it turns, okay, now this is where it gets, this is, okay, as a hint for what you can learn on your own when you go do this, and then come to report back to us, okay? Not only does time get messed up, so does distance in the direction of travel.
Because that's part of the equation.
Yeah. So suppose that Betty has a machine on her train that puts a little dab of paint on the track every second. Okay. Boop, boop, boop. Maybe they used to have water clocks. You ever seen a water clock? It just drips water at a certain rate.
Mm-hmm.
And then, I don't know, when the thing fills up, it rings the alarm or whatever, or it runs. But a water clock is a real thing. And I remember doing this in physics in high school. We had little cars that had a hole in them, and you could put a little drippy water thing on them, and we would roll these cars down a ramp, and they would drip water every certain number of seconds, and you would see that as they went down the ramp, the distance between them got bigger and bigger and bigger.
Because it's accelerating.
Right. So imagine Betty's got one of these machines on her very fast moving train car. And what it does is it puts a little dab of paint on the tracks once every second. Boop, 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 like that. Okay. And since she's traveling at V meters per second, right? So since she sees the tracks moving past her at V meters per second, she will see these little dabs of paint get dabbed on the track every V meters. Okay.
Right.
She will see a dab of paint. Now, Abe is watching Betty go by on the train track. And to him, Betty's clock is running slow. So the little dab of paint will happen every 1 over the square root of 1 minus V over C quantity squared seconds. It's off by that square root factor thing. Okay. Mm-hmm. Now, if she's, I did the math here on this one. If she's actually traveling at C over 2, at half the speed of light, then the paint dabs will get dabbed every 1.15 seconds relative to Abe.
Right, because to Abe, it looks like she is late in doing it every second.
Yes, her time is dilated, okay? So from Abe's point of view, they will be further apart than they will be from Betty's point of view, okay? This contraction factor, this square root of 1 minus V squared over C squared, is called the Fitzgerald contraction. Okay. And it applies that to everything that Betty sees when she's traveling at these really fast speeds. All the things that have linear distance in the direction of travel, get shrunk by that Fitzgerald contraction thing. All right. Now, these are just a few things that you can reason out with a thought experiment. And we could do more of these, but then I have to start reading equations to you, and it gets really, really hard for you to pick them up because you're driving and doing those things.
Right. And you probably have to pull over and pull out your notebook and sit there and contemplate life for the next 2 hours. And you got places to be.
Right. And meanwhile, but you could do that because everybody else is going to be doing that too. Just pulling over the side of the road. You were like, you listen to the buff, and
and you'll all be in the same inertial reference frame of V equals 0.
That's right. And you can't even test it. So all sorts of wacky things happen. All right. You gain mass when you start going really fast, and that's general relativity. And there's all sorts of wacky things going on with gravitational fields and accelerated reference frames. And but we're not going there. We're not going to go there. We're going to stop here at this point. And if you want to learn more, then you should go read those books and those web pages and those things. So let me conclude the light thing this way, Harry. Okay. This is really wacky stuff. Okay, that's thing 1, which is kind of cool. That's thing 0, probably. Okay. Light travels really fast, but it's not instantaneous. It does have a finite.
And in the grand scheme of things, it's relatively slow.
Meaning what?
Well, meaning the universe is really big.
The universe, yes. Well, it's not fast enough to get to the edge without a while. I mean, the universe is really big. Yeah. Right. Okay. Light behaves as a wave, but it doesn't require a medium to carry it. And this is one I've been thinking about a lot while we've been recording these episodes. Is remember, a wave is just energy, and you can only see the wave or the energy by what it makes other things do. Mm-hmm. So you only see the light blip when that that electromagnetic wave hits those pieces of pigment in your rods and cones or whatever they are in your eye, and they get jostled, and then your eye brain system, the optic nerve and all that stuff, gets triggered, and then you see it. And that's the only time you see it. So I guess I think of it as a disturbance, or a potential disturbance that disturbs things once it has something to disturb. Like it might hit the pigments in the paint on the wall and come back as a color into, and then bounce off that thing and come into your eye and disturb that, and you get appeared as a color. Just like a wave in water, it doesn't move the water; it just lifts the bobber up and down as the wave goes through it, and the wave on the rope moves the rope, but the rope doesn't go anywhere. It stays tied up to the doorknob. Okay. All right. So light behaves as a wave and does not require a medium to carry it. People have been measuring the speed of light, or at least trying to, for a really long time. Okay. Think of all the people we've talked about. With lanterns and Galileo, trying opening them up, close them real fast. Okay. Romer and the eclipses of the moons of Jupiter. Remember that discussion? How he realized it? Okay. Bradley and his updating of Romer's work. Fizeau and Foucault and the spinning tooth, wheel, and mirror. Now, somebody has asked us, how did they measure the rotational velocity of the tooth mirror, the tooth wheel, and the mirror? And the answer is, I don't know. That may be a lesson for another day. I don't know how long tachometers have been around. And I had a speedometer on my bike, Harry. Did you have one? Did you ever have a speedometer?
No, I just put playing cards on the back so it sounded like a motorcycle.
Well, okay. But that's the thing. Okay. And what you would do when back in the day, you would have this thing that went on the hub of your front wheel, and it spun around, and there was this cable, a rotational cable that came up through a housing to this big thing, probably 2 inches across. And I guess it had all sorts of gears inside. And the faster the wheel spun, that rotational energy got pointed somehow to a needle that represented this velocity. Now, I don't really know.
You'd have to calibrate it to the diameter of the wheel,
of the wheel,
kind of thing.
And so I don't know, but that's how a tachometer works. And my guess is that they've had things like that, or they had something that was relatively stable that they could turn, and they geared it up multiple times, and they just had somebody cranking on that, trying to get it going really fast, and they tick, tick, tick. I did 6 times. I did it at whatever speed, and or maybe they had machine. They have had put little governors on there to keep the speed constant, and you can adjust those. And,
Yep.
Okay, so anyway, so I don't know how they did it, but that's the thing. And Michelson at the Naval Academy and all the work he did. This has been a fantastic journey. I remember doing this over the course of several years when I was in high school and in college. I just this has been very, very fun, and I'm indebted to the University of Virginia and Dr. Fowler for the notes.
It's really interesting that when you are in school, it's really hard to appreciate certain topics because you're being just blasted with all different types of information all the time. Here's your reading assignment. Here's your science assignment. Here's your math assignment. Here's your history assignment. Do them all within the next 3.5 hours.
Yeah, and don't forget band practice, football practice, and the fact that Jenny wants to go to the football game on Saturday night. Right. Okay, and
so were we really learning anything? No, but and then you come and you do this kind of thing where you spend a little bit of time dabbling. I would say a deep dabble into a certain topic, and you can end up learning a whole lot just by reading.
Yeah, I guess when you're
and
little.
Listening.
When you're little, you learn to read, and then the rest of your life you spend reading to learn. So anyway, okay. And the last thing is, if you travel at near light speeds, you will experience time dilation and all sorts of other wacky things. And if you do that, congratulations, because I'd love to know.
Yeah, if you're painting the cosmic highway, the lines on the cosmic highway, I don't know if you should go really slow or really fast.
Yeah, that's good. That's a good question.
Yeah,
because the lines may appear to be dots for somebody traveling really fast. So.
That's right.
All right. Anyway, that's where we are. That's light. Thank you for sharing your journey with us. It has been a joy, but a lot of work, but a tremendous joy to think about these topics again.
Yeah, we thank you for joining us. Remind you to seek the good, live virtuously, and flourish, and enjoy the adventure of life. It's going to be a great day.